Video 2 of today. Don't want to be late with the second one. I apologize again. So, Chapter 8, Lesson 2. Solubility rules is what we're talking about today. So, aqueous solutions. Sounds kind of like aqua or agua, doesn't it? Alright? Now, that means they have water as the solvent. Water is many times called the universal solvent because it can dissolve so many things. All right? It's considered the universal solvent because it can dissolve so many things. Today we hope to find out why. Well, let's look at our bonds that we've got. Let's revisit that. Covalent bonds. They create molecules, but there are non-polar covalent bonds. Electrons are shared equally, no charged ends. Everything is good and equal. Polar covalent bonds. Hydrogen and chlorine. The electrons unequally shared. Charged poles, a positive end and a negative end. Ionic bonds. Ions are created and then attract. Ions are electrically charged, so there's a positive end and a negative end. Just to remind you, water is a polar covalent bond. There are positive areas and a more negative area. I think that's going to come into play. So, with our polar covalent bonds and our ionic bonds, the charged part of the bonds are attracted to the oppositely charged parts of the water. The charged part of the bonds are attracted to exactly the same thing. Since they have charged areas and they have charged areas, those charged areas of the water want to attract to them. This causes the water to move between molecules and to get to the charge it's attracted to. The same thing happens over here. We get those charges, negative and positive attracting, and that's what allows the solubility to happen. Now what will dissolve? Like dissolves like. Like a polar dissolves polar, water which is polar and salt which is ionic. Oh, they both have charged areas, they'll dissolve. Water which is polar, sugar which is polar. Oh, both have poles, they'll dissolve. Nonpolar dissolves nonpolar. Soap has a nonpolar end and oil is nonpolar. Therefore, they dissolve one another. However, nonpolar cannot dissolve polar. Water is polar, oil nonpolar. Vinegar is polar, oil nonpolar. The oil and vinegar, or the oil and water, stay separated, as you can see with this picture. How much will dissolve? Which one will have the most dissolve? Well, let's see. Solubility. That's what describes how much will dissolve. It's a measure that says how much solute dissolves in a given amount of solvent. Most items are affected by temperature. There's a very few that aren't. And some are affected in ways you may not expect. At least that's what I learned. Highly soluble means a large amount can be dissolved. So 63 grams of this potassium chromate in 100 grams of water. That's highly soluble. Not very soluble means a small amount can be dissolved. Like 0.00025 grams of barium sulfate in 100 grams of water. If it's this low, it's said to be insoluble or not soluble at all. Of course, there's things that range from the very high to the very low. Liquid solid solutions. They're generally affected by temperature. And here's your chart. Some of them, as the temperature increases, you can see their solubility go up quite a bit. Sodium chloride, not so much. A small rise, but not much. And there's even some where these dissolvability or the solubility goes down as the temperature goes up. Those are rare, but most of them as the solubility goes up as the temperature goes up. Now when we think about liquids and gaseous solutions, temperature doesn't generally affect them, but pressure does. So, as the pressure goes up, the solubility goes up. This comes into place when we're canning drinks or other things like that, especially carbonated ones. They put extra carbonation in there, which increases the pressure. If the pressure is increased, that liquid can hold more of the gas. But when you release that pressure, that gas rushes out because there's not enough pressure to make that solubility more. Saturated solutions. Saturated when it holds all the solute it can hold. If you add anything more, it'll settle on the bottom. Could I make the rest of that go away? I guess I could pour the liquid off and leave that there, but there's another way. I want to heat it. The heated liquid can hold more solute. It's completely and fully dissolved now. And if we slowly cool it, the aftermath is that the liquid afterwards can hold more than a normal amount of solute. So it's super saturated. Sweet tea is an example of this. Rock candy solution. We heat it up so it can hold more sugar, and as it cools, some of that comes out. So sweet tea and rock candy, you can think of that. Rate of dissolving. Ways to increase. Well, we could stir or shake. We increase the collision rate of the molecules or the particles, so there's more contact, more dissolving. Increase the temperature. Molecule speed speeds up because of more energy. Collision rate increases. We have more dissolving. We break the solute into smaller pieces. We can get to more surface area of those particles and they'll dissolve faster. Ways to decrease would be to refrigerate. Cool that down, collision rate is reduced, and therefore dissolving is reduced. Concentration tells how much solute is present per amount of solvent. So dilute and concentrated are usually the words we use. If it's not got much, it is dilute. If it's got a lot, it is concentrated. But those, not very specific. We can also be measured in percents. And this is what your doctors, nurses, those people that give IVs and intravenous fluids, they'll tell what percent of the item they want in there and what percent they want to be water, so we can be very accurate. We're going to do that with our cherry juice example. The percent represents how much cherry juice. So you can see we have a very diluted cherry juice drink or a very concentrated cherry juice drink. If I wanted to be more accurate, this has 5% cherry juice, this has 25, 45, 65, and 85% cherry juice. Now the other thing that we can know is, since that is there and we know that the two parts must add up to the whole, water, 95% and 5%. 25% is juice, 75% is water, 45 and 55, 65 and 35, and 85 and 15 makes up that other portion. It's the solvent, there's the solute, a liquid-liquid concentrate, or a liquid-liquid solution. Effects of solute particles. So does anything change when I mix a solute into a solvent? Yeah. So why do we do this? Put the salt on the road. Well, the freezing point of water is 32 degrees Fahrenheit. No, I'm not being very scientific and I'm using Fahrenheit, but I could find that easier than the Celsius. The freezing point of water after the salt, 17 degrees Fahrenheit. So it reduces ice on the road between 32 and 17 degrees Fahrenheit. It'll help us keep our travel plans and have to not cancel as many events. Why do we do this? Put salt in a pot that we're getting ready to boil water. Well, the boiling point of water is 212 degrees Fahrenheit. Boiling after salt is 232 degrees Fahrenheit. This allows noodles to cook at higher temperatures, which doesn't allow them to stick or other things as much. All right, guys, so we talked about a lot of properties of solutes and solvents and how they go together. Thanks. Have a good one.